This video is about block diagrams. It corresponds to section 7.10.2 of the Applied Analog Electronics textbook. Block diagrams are a way of providing two sorts of things. One is to provide an overall structure, an outline, if you will, of a design. And in that sense, it is taking a complicated design and breaking it down into sub-designs, each of which individually is easier to do. So the structure of the diagram, which is the thing that's most evident when you just glance at it, is one important property of a block diagram. The other thing is that there is labeling on the block diagram that tells you not only what each block does, but the signals that come in and go out of each block, what the interfaces are to that block, so that you have a specification not just of the functions, but also of the signals that are being operated on by these functions. Now, normally when I draw a block diagram, because it's one of the first things you do in doing a design, I'm usually drawing them with pencil and paper. And once I've got all the details of the block diagram worked out, then I will draw a neat version for including in a design report. To save some time here, I'm going to go directly to drawing in the tool that I like to use for doing the final versions, and that's draw.io. Now, if you look at the URL up here, it doesn't say draw.io, it says app.diagrams.net. I never remember that new URL they use. The old URL, draw.io, still redirects to here. Okay, one of the nice things about this for a web tool is that it doesn't require you to save your diagrams on their storage. You can use Google Drive, you can use your own disk drives on your own machine. I like to use my own disk drive because I'm usually working as a single user. However, if you're doing something where you're sharing with a partner, then working on Google Drive is very useful because you can share the document. And furthermore, you can both edit the document at the same time if it's on Google Drive. And that can be very useful if you're working together on a block diagram. Okay, but I'm going to do this on my own machine here. Go to Device, click on that, create a new diagram. There's a whole bunch of different styles of what sort of shapes you can draw with and different sort of ways that you can lay them out. Most of that's pretty much useless. I just use basic and blank because that's about all you need for block diagrams. Some of the other things are useful if you're doing other types of diagrams, but because we only use draw.io for block diagrams, just blank and basic, what starts with is fine. And I'll give this a name, example 7.10.2. Let's not use too many decimal points, some 7-10-2, because a lot of computers get confused by periods within file names other than the one that separates off the extension. So, create. Now I've got a drawing surface here in the middle. I've got some objects I can draw with here, and I've got some controls over here for changing how I handle those objects. The objects we use mostly are rectangles, occasionally text if we want to do a title or something like that for the whole thing, triangles for amplifiers, and we'll sometimes use these connectors, though quite often you can create your connectors without having to come down here to pick up this one. So blocks are usually rectangles. In fact, essentially everything we do is either going to be a block that's a rectangle or a triangle for an amplifier. Everything else, if it's not an amplifier, is a block. All right, so let's take a problem that's, say, a pressure sensor. And we want to interface a pressure sensor to a computer. We need to think a little bit about what's our input and what's our output for this overall system. So how do I do an input? An input's a signal. An input's never a block, okay, because blocks are functions that do things to signals. If the input is just a varying pressure, then that's a signal. That's not a block. So I need to start perhaps with an arrow. Let's start with an arrow. Let's put it, up here at the beginning. And because I accidentally picked on this block here. I think I can get rid of that by moving it up into a straight line. There. Okay, so I've got a straight line here that's the pressure signal. And because this is a signal, I need to know something about this. How am I going to choose a pressure sensor if I don't know what pressures I've got? So double click on it to get the text block, and I'll say that this is pressure. Let's say it's plus or minus 50 kilopascals. And we need to know how fast the signal changes, perhaps. So let's say it's a fairly slow changing signal, but not real slow. Let's say less than 10 hertz. So we're interested in all the way down to DC. So we're interested in what is the actual pressure here, but we're not interested in really fast fluctuations in the pressure. Okay, so that's our signal. Now, if I just leave it like that, it's kind of breaking up this arrow, and sometimes that gets a little hard to see whether, particularly if the arrows are short relative to the text. So what I can do is I can click on this arrow and say, let's change the way the text is arranged here and use the baseline at the bottom. And now I've got that text sitting above the arrow, which is often a little easier to work with. So that's what comes in. What do I want coming out of the system? Let's pick another arrow for that. And let's put that one down here. And this one is going to be a stream of numbers. Let's say we want them to be numbers between -1 and 1, minus 50 and 50. This makes it between minus 50 and 50. And how fast is the stream coming out? Oh, let's say it's 30 samples per second. Okay, so those numbers, notice, are going to be inside a computer. So I've got something out here that's in the real world and something down here that's inside a computer. I need to now figure out what goes in between these two things. So how do I do that? Well, I'll have a pressure sensor that'll take the pressure into an electrical signal. Then I'll have some amplifiers, perhaps, to make the electrical signal bigger. Then I may have an analog to digital converter. I might have something that samples it, data logger, a whole bunch of boxes. So let's start putting some of those boxes together. I can take a box here and just drop it down here and say this is going to be my pressure sensor. And I can at this point say what the sensitivity of the sensor is. If I have some family of sensors in mind, I might know roughly how sensitive they are. Or I could leave that for a little bit and say, well, what's the voltage output going to be? Depending on how you're doing the design, you may have different ways of doing this. Because there are fewer choices on the pressure sensor than there are on voltage ranges, it's probably easier to say, well, let's look up a pressure sensor and pick one. Here I'm just going to make something up. Say that's 2 microvolts per Pascal. Now, I don't know that there's a real pressure sensor that does that, but it seems plausible. And then what comes after the pressure sensor is going to be an amplifier. All right, so connecting these two, I need to have, well, what's the signal I'm going to have here? What comes out of this pressure sensor? Well, if I've got plus or minus 50 kilopascals and it's 2 microvolts per Pascal, I can multiply those together to say there's 100 plus or minus. And I might decide, okay, this signal, most of the pressure sensors that I have available, maybe the differential output, so I might say that this is a differential signal. It just runs on 2 wires, not on 1 wire. But the signal is still just a single line on the block diagram, because the lines on the block diagram are information-bearing signals. They're not wires. So this could be 2 wires. It could be a fat cable with 100 wires. It's just saying information is flowing from the pressure sensor in this encoding to this amplifier. Now, the amplifier is going to have a gain. I don't know how much gain. Depends what the output voltage is. I could also put one more thing on this one, because I do know one thing about this. And not just that it's differential signal, I also know that it's less than 10 hertz. So I can keep that information here with the signal. All right, what comes next here? Well, I'm going to have to take the output of this amplifier and I'm going to have to put it through an analog to digital converter. So let's put in that analog to digital converter. And we can put in some specs on here. Say it's a 16-bit analog to digital converter, and that 16 bits is over a range of 0 to 3.3 volts. Okay. That's typical, for instance, of what we get on the TCLC boards that we use. All right, so now I'm going to take the output from here and bring it around to there. I can now look at, well, what does this signal have to be? Because this is 0 to 3.3 volts on the range for that analog to digital converter, I need to make sure that the signal here stays within that range. And let's just say arbitrarily, let's make it 1.5 volts plus or minus 1 volt. And again, less than 10 hertz. And to move this block here, I have to move it manually this time rather than, let's put it over here where it's easier to see. All right, so this is now telling me that I got a 1.5 volt plus or minus 1 volt signal coming out of here. That now tells me, oh, this amplifier, I've got plus or minus 100 millivolts coming in, I've got plus or minus 1 volt coming out. That tells me that the gain here has got to be 10, so I can fill that in. And notice that quite often when I'm doing this sort of design of a block diagram, I'm working kind of from the ends in. I'm not necessarily marching strictly left to right because I have to know where I'm headed as well. So I didn't pick the gain first. I figured out what I needed and then picked a gain based on that. Okay, but this also says I need a 1.5 volts here. Where'd that come from? How did that 1.5 volts come in? I'll need something else perhaps to generate that 1.5 volts. So I'm at the top of the page here, so I need to select everything and move it down to give me some more room at the top of the page here. All right, and I'll put in another box up here. I might as well line it up with these other ones and say this one's going to be a 1.5 volt reference. I have a circuit that generates a 1.5 volt reference, and I will take the output of that and feed it into the side of the amplifier. And there's a difference in an amplifier between things that you put in the base of the amplifier here, the input side, the things that you put into the top and bottom sides. Same thing for any block, actually. The main information flow is left to right through the blocks. And so the inputs are on the left, outputs on the right. The things like reference voltages, control parameters, things that are not the information-bearing things but that control the function of this block, those come in through top and bottom. Power supplies come in through top and bottom. Here we're not showing the power supplies. Sometimes they're done in block diagrams, sometimes not, depending whether or not they vary in different parts of the block diagram. If you have different blocks with different power supplies, then it becomes very important to indicate which power supplies go to which blocks. If it's all on the same power supply, then the power supply may be omitted. Depends on the purpose of the block diagram. What part of the design are you trying to summarize here? Okay, so I've put this thing together now, and notice that my analog electronics, the things I would actually put in the schematic, maybe just this part of it. The analog to digital converter may be off the schematic for the schematic because it's not part of the analog design. Or if I was doing a board that included the digital parts as well, then it might be part of the schematic as well. So the schematic and the block diagram don't necessarily correspond in their scope. Now, the analog to digital converter by itself doesn't produce a stream of numbers comes close. So it might be that this analog to digital converter is part of a microcontroller, or it might be connected to a microcontroller. Let's pretend here that there's a separate microcontroller, and actually, for this one, we'll want a bidirectional connection, because communication back and forth with the analog digital converter, you have to tell the converter to start, you have to get the number from it. So that may very well be one where we want an arrow on both ends for a bidirectional communication. And that might be SPI connection is one protocol that might be used for that. And again, I want to have the text above the line here. Sometimes it's a little hard to click on things. It did not seem to move it up the way I expected it to. Move it up manually. And then the numbers here, I can just take this whole thing and say the numbers now come out of the data logger. And the data logger has to do 30 samples per second to meet now. Here the numbers say plus or minus 50. This data logger actually can't produce that because this thing is producing numbers in some range. We would have to say something about what format these numbers come out in, and there may well need to be some scaling, a multiplication or something going on. So we might need to add, in addition to the data logger, maybe this was too soon. Maybe we need to add a software block. So we can take another block in here. Let's take this thing, separate it from there and say, put it on, oops, put another block here that is scaling, and actually we can take this whole thing and move it over here, draw an arrow from here to here. Now the style of that arrow is wrong because I no longer want a left-hand arrow. This is one way. And the scaling, we could take what does this data logger produce? This might be in the range plus or minus 32,768, and we can figure out what the scaling is, or this might be in the range plus or minus 1.0. Also, this was plus or minus 1 volt here, but this one may vary 1.65 volts plus or minus 1.65 volts. So there might need to be some math figured out for what scaling do we have to do. And notice that this is a software function here. We've already gotten the data in a stream of numbers. We need to say what that stream of numbers comes out being, and that might depend on what this analog to digital converter does, and then figure out the appropriate scaling here. I will leave that as sort of an exercise for the reader. Now we've got this full block diagram. We can fit the whole thing. Where's the zoom? And zoom out a little bit. Okay, so now you can see on the whole page what the thing looks like. And you can take this thing and save it in various formats. In addition to just saving it in the format that you can continue editing it, you also have export as. And I recommend for this class exporting as PDF, because then you can incorporate that directly into your LaTeX files and have all the fonts at full resolution and everything. But I'm not going to bother doing that right now. I think this has given you enough of an idea of what the block diagram is about. Important concepts. Blocks are functions. They're not components. They don't have part numbers. They're telling me what does this thing do, not how is it implemented. The how it's implemented that goes into the schematic. Every line here should have a label. And you notice that there's 2 lines here that don't. This one should be, this one up here, that should have been labeled 1.5 volts so that I didn't have to look to see what it was connected to to figure out what it was meaning here. Similarly, this line down here isn't labeled. In order to figure out what the scaling is that I need here, I need to know what's the range of the numbers here. So I need to have a label on this line as well. So this is an incomplete block diagram. It's not finished. But the blanks here are ones that if you provided them on a block diagram you gave me as part of a finished design report, I would say, you're not done. You didn't tell me, what's this? What's this? I expect every line to be labeled with the appropriate information. Now, when you're in the process of creating the block diagram, quite often, well, I'll leave this later. I know that I got to do some sort of scaling here, and I got some sort of signal here. I know what I want coming out here, but I don't quite know yet what's coming in here. It depends on what this data logger does. And so once you start thinking this more about the data logger and figuring out what its constraints are and what it's capable of doing, then you go, oh, well, that'll give me this range of numbers here, and now I can figure out what the scaling function is here that has to be done in software. And so what I expect to see in the finished design report, every part of this thing should be complete and accurate. And I should be able to look at any one block here and just look at the things connected to it to see that it's consistent. Is a gain of 10 here consistent with the plus or minus 100 millivolts and 1.5 volts plus or minus 1 volt? 100 millivolts, 1 volt, yeah, scales correctly. Gain is 10. And the 1.5 volt reference here, if I had this properly labeled on the line here, would give me the 1.5 volt offset for the single-sided output on the amplifier. So again, there's a consistency check. In fact, one of the things I do when I'm grading design reports is I go through the block diagram and I do a consistency check on each block. And if it's not consistent, if you'd said the gain is 20 here, I would know there's an error in your design, a serious flaw. And you should be able to find those serious flaws yourself too, just by doing a consistency check at each block. Does the function of this block match the input and the output? Is there enough information to be able to determine? Is the sensitivity here consistent with the range of the pressure coming in and the range of the voltage coming out? That's the sort of check that block diagrams enable, and you should be doing them. Make sure your block diagram is complete and consistent. This one, the fact that there's some blank arrows here tells me it's not complete. And because I don't have any label on this arrow, there's no way that I can get this scaling function right because I don't know what it's supposed to do. So make sure that you've got complete labeling, because you can't implement the individual blocks unless you know what the blocks are supposed to do. Okay, that's probably enough for now. We'll talk about schematics in a subsequent video.